propagation of light through the water column, light fields within and leaving the ocean, and any optical applications, practically any ocean optics science topic or application depends on interactions of light with marine particles. So here on the slide, I indicated several broadly defined optically significant categories of constituents of seawater, molecular water, inorganic salts, dissolved organic particles, and suspended particulate matter, which can be divided into several broadly defined categories: plankton, microorganisms, organic detrital particles, mineral particles. I also indicated explicitly a separate particulate component, colloidal particles. These are the small particles, generally smaller than 1 micron, which are by far the most abundant particles in seawater. And air bubbles can also be considered as part of this constituent, particulate constituent. But even within this, each broadly defined particulate components, there are very, very many types, diverse types of particles of different sizes, chemical compositions, functions in the ocean, and each of these particle types absorb and scatter light differently. So it is very important to develop some basic understanding of how individual particles of different types absorb and scatter light, and this will be one of the main goals of this lecture, to introduce you to theoretical and experimental facts about absorption and scattering by single particles of different types. So as I indicated, you can see here in this slide that even within broadly defined categories such as mineral particles or plankton microorganisms, particles differ enormously in terms of sizes, shapes, internal structures, and which all affect how each of these different particle types absorb and scatter light. And it is fundamentally important to have some solid understanding of single particle optics if you address any scientific question using ocean optics or any applications including ocean color remote sensing. So essentially every aspect of optical applications to this in the study of the ocean depends on how very, very many types of particles absorb and scatter light, and how they produce the net effect, which typically is what we measure. We do not measure optical signal coming from individual particles, but we make measurements on finite volumes, inherent optical properties that you've already learned during this course, or apparent optical properties such as remote sensing reflectance. They are all referred to finite, smaller or larger finite volume of seawater, which consists of very, very many particles and molecules. So because of the complexity of the particle types and composition and the different optical properties, the problem is extremely challenging. So I will try to expose you to this complexity, and I would like to mention that most likely, much of the material that I will present today, and of course I will have to, within an hour and a half, I cannot cover each and every aspect in great detail, but I presume that much of that material that I will present will be most likely new to you. So I would like to offer my availability. If you find it of interest, I can be available for a separate online Zoom or something session, question-answer question, QA session, either during the course, which may be difficult because there are 13.5 hours difference between us, and the schedule of the course is really full. So, but I'm available even after the course. You can reach out to me. We can make session if you're interested in if you have questions and would like to gain a more in-depth understanding of the material that is covered in this lecture as well as my 2 previous lectures. So we will begin by establishing the linkage between the single particle optical properties and the bulk optical properties of particle suspension. And this linkage is established, is demonstrated in this slide, in which I show the relationship between inherent optical property which is a bulk optical property in a sense that it represents the contribution by a collection of particles to the measured absorption coefficient of seawater. And of course, this concept applies to any other inherent optical property. It could be total scattering or backscattering, volume scattering function, or even elements of scattering matrix, Mueller scattering matrix that accounts also for polarization properties, inherent polarization properties of particles. But we will just, for simplicity, we will just discuss this concept using the example of absorption coefficient. So we can see on the left-hand side in the blue, absorption coefficient, which is a bulk quantity, is, and let's assume that we have an assemblage or collection of identical particles. So this can be a single phytoplankton species, just to make an example. And so the bulk properties are absorption coefficients on the left-hand side, and it is related to single particle properties, which are in the green through this equation, which looks quite simple. Mathematically, it's just the product of the number concentration of particles. So this is per unit volume. So this is number of particles per unit volume, N over V. So this is another bulk property, and these QA and Q and G are single particle properties. QA is the single optical property referred to as efficiency factor for absorption, and G is a measure of geometric size of particles, specifically is the projected area of the particle. And the product of Q and efficiency factor and G is called optical cross-section, in this case, absorption cross-section sigma A. And you can see that sigma A can be, from this equation, can be derived as a ratio of A, which is a bulk property, and the concentration of particles, N over V. So these are measurable quantities, A and the particle concentration. So you can envision experiments in which you measure the total absorption coefficients of a collection of phytoplankton species, specific phytoplankton species. You can measure concentration, and you can derive optical cross-section that represents a single particle derived from that population. Or if you measure also size distribution, you can also additionally obtain a Q factor because you know the projected area of the particle. It's important to know that I assume here that all particles are identical. If you have a single phytoplankton species, some phytoplankton cell, all phytoplankton cells will not be identical to one another. They may differ slightly in terms of size, for example, but generally they will be similar. The population of a single species will exhibit similar size and similar efficiency factor for absorption. So we can just this equation applies in a sense that we can say that it's meaningful to determine single particle efficiency factor or cross-section, which represents an average cell from a population of a single species phytoplankton or any other type of particle for that matter. And here the slide also shows the units for different quantities. So obviously absorption is per meter, concentration of particles per cubic meter. Absorption efficiency factor is dimensionless. Absorption cross-section is in units of meters squared, and area of geometric cross-section is in meters squared as well. So if we assume, and for much of our discussion, we will assume a simple model just to make our discussion simpler. We will assume spherical particles just to understand the concepts in sort of more straightforward manner. We will assume that particles have a spherical shape, so the cross-section is just pi over 2 times d squared, where d is the diameter of the particle. And I omitted here the lambda argument, the wavelength argument. Of course, all optical quantities are a function of lambda, so absorption coefficients or efficiency factor for absorption or cross-section for absorption are all functions of wavelength. So let's focus now our attention on optical efficiency factor Q sub A. So absorption efficiency factor for a single particle is a fairly straightforward, simple concept. Which is illustrated in this graph. It is defined as the ratio of power absorbed by a particle to power which is intercepted by the projected area of that particle. So you can envision here a beam of light incident upon the particle, and so the projected area intercepts the power that is F sub 0. This portion of that power will be absorbed, and absorption cross-section is just Q sub A times G, and Q sub A is F sub A, which is that portion absorbed over the power that is being intercepted by the projected area, and it's dimensionless. So for spherical and homogeneous particles, it is possible to calculate exactly how efficiency factor for absorption, and you can use the ME theory, which I've discussed, which is an exact solution to electromagnetic problem for spherical homogeneous particles. Homogeneous means that chemically the particle is uniform in terms of its interior. So you can calculate the behavior of efficiency factor of a single particle as a function of physical properties of particle, and these physical properties, the most important ones that determine absorption is the size of particle, which is shown here as a diameter d, as well as the strength of absorption of material that is or substance that is forming the particle, and that is quantified through this absorption coefficients of the substance that is forming the particle. So it's absorption coefficient of that substance, A sub S, is essentially the same concept as you learned what absorption coefficient for any finite volume of seawater might be defined. But here we are interested only on the fraction of absorbed power per incident power per unit path length within the interior of the particle itself. So that absorption coefficient can be actually a quite large number. And these two quantities are combined, the product of size and absorption property of the particle. The product gives us the so-called absorption thickness. This is a parameter that combines these two that drive absorption efficiency. You can also rewrite this product in terms of the relative particle size times the so-called imaginary part of refractive index. The relative size of particle, I've already defined it in one of my previous lectures. In optics of interaction of particles, light and particles, what's important is the geometric size relative to light wavelength. So that's what it essentially is, diameter of the particle divided by the light wavelength. But because the particle here of interest to us is suspended in water, we know that light wavelength in water is decreased respect to light wavelength lambda in vacuum by refractive index of water. So that's why refractive index is here of water, and W is refractive index of water. Now, so lambda is the size parameter, and the imaginary part of refractive index is directly related to this absorption coefficient. And I have really no time exactly to discuss the origins of imaginary index of refraction. But basically, it has to do with the description of wave-like description of electromagnetic radiation that propagates through the absorbing medium, and you can express this harmonic wave-like form of radiation in terms of complex numbers, and as the electromagnetic wave propagates through the absorption medium, the amplitude of electric field is being damped, and in this notation with complex numbers, this imaginary part occurs as which represents this damping of electric field as the electromagnetic wave propagates through the absorbing medium. But the bottom line is a real physical quantity. As you can see, it's related to absorption coefficient of substance that is forming the particle. So note that so we use here the one parameter rho prime, which combines geometric size, absorption coefficient of particle, and lambda is also involved. So if we plot the solution to the problem, how QA varies as a function of rho prime, we obtain this nonlinear function that initially increases with rho prime rapidly and then flattens and approaches the asymptotic value of 1. So if rho prime is large, so either we increase the absorption of the particle, the substance is, let's say, loaded more and more with pigments, or the particle becomes larger and larger, and we fix the wavelength in this consideration, we are approaching efficiency of 1, so meaning all light intercepted by the particle is being absorbed. So basically, particles that are small in size or have weak absorption will be in this portion of the curve, and as we move on, we are approaching higher efficiencies. So for example, very small phytoplankton cells will be somewhere here, and larger phytoplankton cells may be somewhere there, especially if we are within the absorption bands. If we are outside absorption bands, the efficiency will be always low. This nonlinearity of this function is actually quite important. There's some other information shown here explicitly what the sizes could be if we fix absorption coefficients, if we fix lambda. So we can see that particles in this range are relatively small. So to the left of the first tick mark is particles lower than 4 microns, for example. If we assume wavelength of 430, so it's close to the blue absorption bed of phytoplankton, and if we assume that this is a phytoplankton cell that exhibits this relatively high absorption coefficient in the blue band. But I want to mention the implication of changes in the slope of this function if we move across this function. So if phytoplankton cell is small, it has a capability to either increase its size, but any species, of course, is constrained of how much it can increase its size, or it can synthesize more pigments to increase its absorption efficiency. However, if we begin to consider larger phytoplankton cells, so to begin with, this larger phytoplankton cell maybe is in somewhat flatter portion of this curve. So it actually, the strategy to increase efficiency is not as efficient, because if this larger cell synthesizes more and more pigments, so increases A sub S, it can increase efficiency, but not as efficiently as if it were in this portion of the relationship. So the next few slides will give us some example data of absorption efficiency factor, in this case for 2 phytoplankton species. And the data I will present were derived from lab experiments with single phytoplankton species, with cultures in which spectrophotometric measurements of the spectra of absorption coefficients were made. Also beam attenuation coefficients was measured spectrally. So if you take the difference between beam attenuation and absorption, you have total scattering coefficients determined experimentally, and also cell size distributions were made. So we can, from these measurements, we can determine these mean efficiency factors representing an average phytoplankton cells within a given population of cells that have been subject to experiments. So you can see here examples for 2 different species, Prochlorococcus and Synechococcus. So these are small cells. Prochlorococcus is about less than 1 micron in size. You can see on the right-hand side size distribution measured on several cultures, different strains of Prochlorococcus. So peaks about 0.6, 0.7 micron in size, and below we see Cyanobacteria synechococcus. So these are somewhat larger cells, but still very small, either slightly below 1 micron or slightly larger than 1 micron. And you can see these experimental determinations of efficiency factors. So for Prochlorococcus, so we can see typical spectrum of absorption, but efficiency factors, for example, in the blue range from about 0.2 to 0.35, so 20 to 35% or so efficiency of absorbing light intercepted by the cells in the blue. And accordingly, you can see spectral changes in the red is less. And for Synechococcus, you actually see somewhat smaller values, even though the cell is larger. These cells apparently had, well, for sure, this is evidence, these cells because have lower efficiency factors than Prochlorococcus cell, but Synechococcus is larger, so absorption coefficient, or by the way, this absorption coefficient of substance is related to intracellular pigment concentration. In other words, the concentration of pigments per unit volume of the cell. So in this case, size is one determinant, but also intracellular concentration of pigments must have been lower for Synechococcus cultures than Prochlorococcus. So the absorption coefficients was lower, so efficiency is lower for Synechococcus than Prochlorococcus. And here is the compilation of data at a single wavelength, of experimental data superimposed on or shown along the theoretical prediction of efficiency factor for spherical particles, internally uniform spherical particles. This is the dashed line. The experiments were done with multiple phytoplankton cultures, but also a few other types of organisms that are essentially non-pigmented, non-photosynthetic, so heterotrophic bacteria, non-photosynthetic flagellates and ciliates. So these microzooplankton cells, and flagellates are about 4 micron in size, ciliates about 30 micron in size, but heterotrophic bacteria about half a micron in size. Other data points are for different phytoplankton species. And you can see the intent of this graph is to show that these experimental data follow the theoretical prediction fairly well, even though the theoretical prediction is for spheres, internally uniform spheres, and all these particles are not not spherical, and they are internally non-uniform. Nevertheless, we see general consistency here. All these data are for a single wavelength of 675 nanometers. So this is the wavelength where chlorophyll A has the secondary peak in the red. And let us now turn our attention to scattering efficiency factor for a single particle. And this concept is similar to the absorption efficiency. So here we have geometry for determining the efficiency factor. So again, the particle is illuminated by a beam of light where the power intercepted of particle is F radiant power intercepted by the projected area of the particle is F sub 0. And some of that power will be scattered. For example, here it's shown at a scattering angle psi, but scattering will occur at all angles. And so efficiency factor accounts for power being scattered by that particle in all angles. So it's an integrated scattered power, F sub b. And the ratio of that power, scattered power, to the incident power intercepted by projected area is defined as the scattering efficiency factor. Again, this is dimensionless quantity. We can also define similar quantity for a specific scattering angle. We would call it then differential efficiency factor, because it just is associated with power scattered at a specific direction. And again, product of scattering efficiency and geometrical cross-section of particle is scattering cross-section, which is in units meter squared, because QB is dimensionless, G is meter squared. Now, this slide is a little bit more complicated than the previous one that showed the dependence of QA on physical properties of particle. These are the results of theoretical calculations showing how optical efficiency factors, and in this case, we show QA, QB, as well as QC, which is attenuation efficiency, and QC by definition is the sum of efficiency for absorption and scattering. So attenuation efficiency is simply the ratio of the power that is being both absorbed and scattered in all directions to the power intercepted by the projected area of the particle. So Fc over F0 is the attenuation efficiency. So in these two graphs, I'm illustrating QA, QB, QC as a function of one parameter that combines several characteristics of particle, and this parameter is referred to as ρ. It is called phase shift parameter. So without going into details why it is called phase shift, I will just define components of this parameter ρ. So again, we have alpha. So this is the size, the relative size of particle relative to light wavelength. And you can see here another component of this product is n-1, where n is the refractive index of particle relative to water. So because we are considering particles suspended in water, and then we are interested in refractive index of particle not in free space, not in vacuum, but in water. So in other words, this relative refractive index of particle in water is the ratio of the absolute refractive index of particle. So this would be a value of refractive index of particle if it was suspended in vacuum divided by refractive index of water. So if we have if n-1 is different from 0, it means there is a contrast in refractive index between particle and the surrounding water, and that particle will contribute to the scattering. And okay, and the results that we see here have been obtained from, again, using the mi-scattering calculations for homogeneous spheres. So again, we have simplified model, but it just reflects the main aspects of the behavior of changes in this optical efficiency factor as a function of particle properties. So what we have on the left-hand side here is the plot of QC, these upper three curves, and QA, which is here these dashed lines. And actually, there's one more curve, QA, which coincides with this horizontal axis of the graph. So there are three curves for absorption efficiency factors and three curves for attenuation efficiency factors. And these three curves represent three different particles which differ in terms of absorption. Particle number 1 has no absorption. Particle number 2 has some absorption, and 3 has stronger absorption. So because the parameter ρ does not explicitly include any absorption characteristics, it's just size relative to wavelength, and the real part of refractive index relative to water. It has nothing, in terms of what a particle, how absorbing the particle is. We have to add additional parameter, and in this graph, this absorption parameter is just parameterized in terms of the ratio of this imaginary part of refractive index. So that's the absorption and real part of refractive index here. So that's not so important. What's important for our message here is that we have three different particles, one non-absorbing and two that exhibit absorption, and with particle 3, the highest absorption. So non-absorbing particle has QA, which is just right here, particle number 1, along the horizontal axis. And then particle 2 has QA, which is this function that you've seen in one of the previous slide, this nonlinear QA, which is approaching 1 if particle is large, for example, because ρ has lambda. So if ρ is large, it can be due to large lambda. So if particle is large and has some absorption, it will tend to absorb a lot of radiation, or most radiation that is being intercepted by projected area. Now, okay, what's really striking in this graph, you can see that attenuation efficiency is a pretty complex function of particle properties which are embedded here in ρ. And remember that ρ also embeds alpha. So, alpha embeds wavelength of light. So wavelength of light is also implicitly involved in these functions. So, but what we see here is initially efficiency factor for attenuation, which is both absorption plus scattering, increases rapidly with increase in rho, achieves the first maximum and then oscillates and tends to reach an asymptotic value for large values of rho of value of 2. Well, the first striking observation is that efficiency factor for attenuation can be larger than 1. What does it mean? It means that a particle can attenuate more light than is being intercepted by the projected area. At first glance, it may seem like a paradox. How it is possible that particle attenuates more light that is incident on its geometric projected area? The explanation is diffraction. So recall one of my earlier lectures that light can be also scattered as a result of diffraction mechanism. So the wavefront of incident light in the vicinity of the edges of particle will fill the particle in a sense and will bend and will get scattered. So that will explain the fact that that sometimes called extinction paradox or attenuation paradox, that efficiency factor for attenuation can be larger than 1. That's what happens here. But there is also this oscillation. You can see the more absorbing particle, these oscillations are being damped. Okay, but attenuation efficiency is the sum of absorption and total scattering efficiency. So if we take the difference between QC and QA, we are getting these patterns of behavior of Q sub B, which is efficiency for total scattering as a function of particle parameter rho. And you can see here non-absorbing particle is 1, particle 1. So again, it looks exactly like the curve 1 for attenuation efficiency, because Q sub A is 0. So Q sub C equals to Q sub B. So this is non-absorbing particle. If we add absorption to a particle, you see that this efficiency for scattering drops down, and which makes sense. So if you have a particle that is more and more absorbing, then you have less light being available to be scattered. You can interpret that simply, that effect which you see here. And you can also see that if rho is large, and rho can be large either if the particle is very large relative to light wavelength, or particle has very, very large refractive index, or both. So let's just assume that refractive with some, typical refractive index, we can fix it. Let's also fix wavelength, which is here embedded in alpha. Remember that alpha is inversely proportional to wavelength, but it is proportional to the diameter of particles. So if we move to the right along the axis of rho, and if we fix wavelength and refractive index, we are increasing the diameter of particle. So for large values of rho, we are in the domain of the so-called optically large particles. You may recall that I described in my previous lecture one of the approximations, theoretical approximations for optically large particles is the geometric optics. So particle scattering by particles in this geometric optics domain is driven by, or well approximated by, combination of reflection of the surface, then refraction into the interior of the particle, internal reflections and refractions, so multiple reflections, as well as diffraction. Okay, so we can explain this extinction paradox nicely here, because if we are in the domain of very large, optically large particles, large rho, we can see that the highly absorbing particle tends to have efficiency factor for scattering of about 1. But also the very same particle, if it is very large and it includes some pigments, absorbing substance, it also tends to absorb all light that is incident upon its projected area. But this particle will attenuate twice as much light that is being intercepted by a projected area. So half of it comes from absorption, another half from scattering, and that scattering contribution comes practically entirely, virtually entirely from diffraction, because all light has been absorbed within the particle, so there is, you know, no light really that can escape the particle through these internal reflections and refractions. But of course, there is some reflection of the exterior of the particle at the first interaction with particle, but mostly this value is driven by diffraction. So I hope, you know, this can get complicated if you think about the combination of different characteristics of particle, but these are very powerful theoretical concepts that allow us to interpret our measurements and absorption and scattering properties of different types of particles, different species of phytoplankton, other biological particles, mineral particles, and so on and so forth. So also it can allow us to interpret our spectral measurements, because remember that alpha is defined. I can go back here just to remind you. Alpha is defined as d, essentially the diameter of particles, so it's a geometric size divided by lambda. So if we look at this curve, lambda is here. So if we fix size and if we fix refractive index, so let's say we choose a specific type of particle, specific species of phytoplankton, and we look at the spectral behavior of attenuation, absorption, or scattering. So that spectrum will coincide with a certain portion of this theoretical curve. So spectrum can be on this ascending portion of theoretical curve. The spectrum can be somewhere here around this first maximum, or maybe on the descending part, depending on rho parameter. So depending on what the size and refractive index, our spectrum can coincide with any portions of this theoretical curve. It can also coincide with the portion of the curve that is flat, so the spectrum will be flat. So this will be a very powerful tool, theoretical tool, to interpret spectral measurements of absorption and scattering of different particles. And I will, in a moment, show you examples of this interpretation. Now, okay, I've been talking here about calculations for single-sized particles. Single-sized particles are referred to as monodisperse. They form monodisperse population of particles. So if you have an assemblage of particles that have identical size, we refer to this assemblage as monodisperse. And if you change a little bit, if you have realistically any, for example, species of phytoplankton, it's not perfectly monodisperse, as I indicated before. So we can have, for example, a Synechococcus cyanobacterial culture, and it will be slightly polydisperse, as it's shown here. But generally, the degree polydispersity is the width of the size distribution. But the width of size distribution for single species is relatively narrow. But still, this small degree of polydispersity is quite important, because what it does, it is damping these oscillations. So if we assume that some type of particle that has a central or modal diameter, and if we allow this slight variation in size around this modal diameter, then the theoretical calculations for this small degree of polydispersity will change these theoretical curves in a way that we damp these oscillations. And for example, we see 1 to 3 are just different assemblages that have slight polydispersity added to it. And you can see this, these curves approach the flatness much more readily, and the asymptotic value of 2. So it is enough to have slight polydispersity, for example, to reach this regime where attenuation or scattering efficiency will be flat for relatively large values of rho. And here is the example that demonstrates experimental data of scattering efficiency, again derived from these laboratory experiments for phytoplankton heterotrophic microorganisms. And we are showing here these experimental data again for a single wavelength. So these data are either for 580 nanometers or 550 nanometers. And there are these non-pigmented types of particles, heterotrophic bacteria, flagellates, ciliates, and all other data points were for different phytoplankton species. And for comparison, what we show here are these theoretical curves of scattering efficiency. And one of them is calculated for monodispersed system of particles, and another was for a single size, and another one is just allows the slight polydispersity to exist. So you can see no oscillations here, but still the primary maximum is present here. So we do not expect these experimental data points to fall exactly on these theoretical curves, because we could create very many theoretical curves like this. Like you can see here, for example, we have 3 curves, but you could create a lot more by changing, wavelengths or absorption parameter here. But basically what we see that small-sized particles like heterotrophic bacteria, some of these other points are associated with small-sized phytoplankton, Prochlorococcus, Synechococcus, flagellates about 4 micron in size. Some larger-sized phytoplankton species are here. Ciliates about 30 micron in size are here. So they are very close, to this flat portion of the Q sub B versus rho parameter. And you can see, for example, bacteria have very low efficiency for scattering, but some other particles or species have efficiency for scattering much larger than 1, even close to 3. So consistent with what theory generally would predict. And so right now, I would like to discuss the interpretation of measurements or experimentally derived spectra of scattering efficiency for different phytoplankton and heterotrophic microorganisms in terms of the theoretical background that I've just described. So in these graphs, we have these Q sub B efficiency factors for total scattering versus wavelength. So we see the spectra for heterotrophic bacteria, Synechocystis, this is a cyanobacterium about 1 micron in size, flagellates about 4 micron in size, ciliates, microzooplankton about 30 micron in size, and 2 species of phytoplankton, that's elongata is about 10, 11 micron in size, and coccolithophore, Emiliania hook slide, about 4 or 5 micron in size. So when you look at these spectra, you may ask yourself the question, why these spectra look like this for scattering? And it is actually quite powerful to go back to our theoretical considerations and attempt to explain what we see here in this experimental data. So bacteria, let's move back here. Bacteria are small particles, so the rho will be small. And because rho involves alpha and refractive index, let's assume these bacteria have constant, more or less constant refractive index, but alpha is size d over lambda. So in other words, lambda, shorter wavelengths of lambda will be higher on the ascending slope, and longer wavelengths of lambda will be lower on this theoretical curve. So in other words, the spectrum of bacterial scattering will exhibit higher scattering at shorter wavelengths than at longer wavelengths, because bacteria are located within this ascending portion of theoretical curve, and they all have low efficiencies because the rho values are small, And that's exactly what we see in experimental data. Increase with Q sub B with decreasing wavelength, but the values of efficiency are quite low. If we go then to somewhat larger species, the raw values will be higher, but Synechocystis will still be in this ascending portion, so it will exhibit stronger scattering at short wavelengths than long wavelengths. 4 micron in size flagellates. Now, still the same spectral behavior with higher scattering in the blue than in the red, but the values of efficiency are now higher somewhere in the short wavelength end of the spectrum between 1 and 2. So, so we are somewhere in this region. So the spectrum extends from the red around 1 to blue edge of the spectrum, which is about 2 for flagellates. But we are still on this ascending slope, and there is more scattering in the blue than it is in the red. And let's move on to the next species. Maybe let's start with ciliates. This is flat spectrum. So what happens here, we are in spectrum is located along this portion of the theoretical curve. And the efficiency is close to 2. That's exactly what we see here in experimental data. And now we have 2 other very interesting examples of 2 different phytoplankton species that have different sizes. This one is about 10, 11 micron in size, elongata. What we see here that scattering tends to increase with increasing wavelength. Maybe this may be somewhat surprising. Generally, you may think that scattering in seawater tends to be either relatively flat or increase towards smaller wavelength, shorter wavelengths, and that's true for collections of all particles suspended in seawater, because small particles generally have this exert important influence on the spectral behavior of scattering by the collection of all particles suspended in water. So that's what you see in seawater, but very many particles that are present in seawater may have scattering, exhibit scattering that increases from short wavelengths to longer wavelengths. And this is an example of particle, is phytoplankton species that has this increase. You can see that scattering also exhibits some features that seem to be like a mirror-like features of absorption. So in the absorption band, scattering is being reduced. So in the blue absorption band and the red absorption band, you can see reduced scattering, but generally the general trend is the increase from short wavelengths to long wavelengths. Why is that? Where is this particle here? This particle will be on the descending slope here. So the raw values for this particle, the combination of size, wavelengths, and its refractive index and absorption will work together in a way that this particle, the spectrum of this particle, will extend over this descending slope. So we will have stronger scattering in the red and weaker scattering in the blue. And finally, we have an example where, apart from the fact that you see the effect of absorption on scattering spectrum by the scattering is being dumped within the absorption bands, the general trend of this Emiliania-Huxley spectrum is such that initially you have, from the blue to green, you have increase of scattering, and then from the green to the red, you have tendency for scattering to decrease. And you have very high efficiencies for scattering here, reaching the value of 3. But the bottom line is that this spectrum of scattering for this particular species exhibits maximum in more or less in the middle of the spectrum. And this is because the spectrum now is located within this primary maximum of theoretical curve. So the raw values are somewhere here in this region, and this is how we can explain the behavior of scattering for Emiliania-Huxley. So I think this is a quite powerful example and also shows the complexity of different patterns of light scattering that can exist for very many different types of particles. What you see here is just six species of microorganisms, but you also see dramatic differences in spectral behavior, scattering property on particles. So this all will together play an important role how the net effect of bulk optical properties in the ocean are being produced by different compositions and concentrations of different types of particles in ocean water. And this graph shows three efficiency factors, QC, QB, and QA for two species. One, Platinomonas. This is a cell that has about 3.4 micron in size, and you can calculate, you can estimate the refractive index for this cell, and therefore you can estimate this size parameter, the raw parameter. So the raw parameter is 3 to 5, so you can see that scattering and attenuation exhibit this general trend with maximum in the middle of the spectrum. So just like from Emiliana Huxley, it's kind of similar, and you can see pretty high values for QB and QC between 2 and 3. Now, if we look at the efficiency factors for cyanobacteria that are about 1.2 micron in size, again, you can calculate for a realistic refractive index, you can calculate the range of alpha, and this range of alpha, which I show in raw, encompasses the range of these wavelengths. So the wavelengths is driving the change in alpha here, from 20 to 35, or raw from 3 to 5. That's how it changes if we change wavelength across the visible spectrum. And similarly, at the bottom, you see the changes in alpha across the visible spectrum, or raw for this particular species. So raw value are relatively small, so we can see scattering and attenuation, which is driven largely by scattering and only to smaller extent by absorption, exhibits this pattern of increase towards shorter wavelengths. The next parameter that I would like to, or optical property that I like to briefly discuss is the scattering function. So up to now, I talk about total scattering, which represents the integrated scattering over all scattering angles. But of course, the scattering function is of tremendous importance for interaction of lights with seawater and propagation of light in the ocean, and also for water-living light fields. So it is important to at least touch a little bit, at least, talk briefly of how the angular shape of scattering function, which can be quantified through the so-called scattering phase function. So we are just comparing the shape of scattering function without accounting for the magnitude. So in other words, this is a volume scattering function divided by its integral that gives us the scattering phase function. And how that shape of scattering function depends on basic physical properties of particles, size and refractive index. So you can see again calculations from Mie scattering theory for different size parameters, 4, 12, 8, 80 and 300. We have fixed refractive index. This is a very small refractive index relative to water, but can be typical of phytoplankton cell. So relative refractive index of phytoplankton cells relative to water are rather small values, like 1.03, 1.05, maybe 1.07, just because phytoplankton cells, like any other life cells, consist largely of water. So significant fraction of internal volume of living cells is occupied by water, and only smaller fraction of internal volume of living cells is occupied by solids, and that determines that the refractive index relative to water is relatively small. The Ln means that these calculations allowed a small polydispersity, so we don't see very strong oscillations in scattering phase functions. You may recall that if we have a scattering on a single particle, then this mechanism that coherent scattering from very many dipoles that contribute to scattering at any given angle. This mechanism involves interference. It can be constructive or destructive depending on the scattering angle of observation. So here we, by using small degree of polydispersity, we smooth these functions so they don't exhibit maxima and minima due to interference. So there are some here. But basically the message here is if we have a small particle, small alpha, we see this function, which is the shape of the function has relatively high contribution of backscattering to total scattering, although forward scattering dominates in all cases here. And if we increase the size, we see the functions are much more peaked into forward directions and are very steep here. And this forward peak here, or forward lobe, is produced primarily by the diffraction effect. So if particles are very large, then this diffraction lobe is very narrow. So the intensity of scattering is dropping very rapidly. If particle is small, then you can see this forward diffraction lobe is wider. It extends to larger scattering angles. That forms one of the bases for inverse methods to derive particle size from forward scattering measurements. But this is beyond the scope of my lecture. On the right-hand side, you see the effect of, we fix in this case alpha, so we fix the size and we change the refractive index from 1.02 to 1.075. And what this graph, the main message here is that in the forward directions, in the diffraction lobe, the effect of refractive index is very weak or practically undetectable here. So diffraction for large particles is very weakly dependent on refractive index. So that's actually a good thing if you want to determine the size of large particles from diffraction measurements, because there is no dependence on refractive index. But refractive index starts contributing to differences in the shape of scattering phase functions at angles larger than about 10-15 degrees, and there is a large difference here in the backward directions. And the tendency is that the higher the refractive index of particle, the particle tends to produce a greater proportion of backscattering in the total scattering. So if we integrate this curve, the ratio of backscattering to total scattering will tend to increase with increasing refractive index. It also tends to increase with decreasing the size, as you see on the left-hand side. And this is an example of simulations of angular shape of scattering. In this case, the normalization is done at 0 degrees, so we can just compare the shapes. But these four simulations are done for parameters that kind of resemble parameters of heterotrophic bacteria, flagellates, ciliates, or phytoplankton species that is about 8 micron in size. So you can see, that small particles tend to have a higher proportion, such as bacteria, higher proportion of backscattering in total scattering than larger microorganisms. And you can see this phytoplankton species is absorbing radiation, so it additionally drives the backscattering especially down, because it makes sense. You have more absorption within the particle, within the interior of particle. It affects the absorption more strongly, affects backscattering by particle than it affects forward scattering by particle or total scattering. So backscattering is affected by absorption by a particle to a larger extent than the total scattering, and total scattering, as we know, is dominated by forward scattering. And another quantity I want to briefly discuss is the backscattering ratio. So it's the ratio of backscattering to total scattering, and these are simulations for particles that have different, as a function, so different refractive index. So for particle 134 have real part of refractive index relative to water changing between 1.02 to 1.07. And there are 3 other particles which have the same real part of refractive index, but there's some absorption being added. That's indicated by this imaginary part of refractive index. And there is also one example, which is for monodisperse size. These 7 examples include slight polydispersity, so these curves are more smooth. But there are a couple of main features that I would like to highlight here. So we are plotting backscattering ratio in the logarithmic scale versus the relative size parameter alpha here. So on the left-hand side, we are within the range of extremely small particles, and eventually here at the very end of on the left-hand side of this graph, we are within the molecular size. So backscattering ratio for molecular scattering is 0.5. So the same amount of radiant energy scattered in forward directions as in backward directions. So we can see this graph starts at 0.5. And as we increase alpha, it starts drop for alpha larger than 1 very rapidly. Initially, in this range of small particles, the effect of size, so the effect of alpha on backscattering ratio is weak. The effect of alpha is very strong, but the effect of refractive index is very weak in this region of small particles, small alphas. But then refractive index begin to also play a major role for backscattering ratio if we increase alpha beyond the value of 5 or something like this. And you see if alpha is on the order of 10 or 100, the refractive index plays a very, very important role in driving the magnitude of backscattering ratio. And the tendency, as I mentioned before, is the higher the refractive index. So particle 4 has much higher backscattering ratio than particle number 1, but the dashed lines are lower. Corresponding dashed line like 3' is lower than 3 or 2' lower than 2, because if we add absorption, then backscattering ratio drops, which I've also indicated just a moment ago. Okay, so let me check time. We have half an hour to go. So I will try to move, as rapidly as possible, but still will attempt to highlight most important messages on subsequent slides. I would like now to provide you with some insight to variability, optical variability for plankton microorganisms, and as we discussed, particle size and refractive index, which we can refer to as complex refractive index, consisting of real part and imaginary part, so both just regular refractive index as well as absorption, are the first order determinants of interspecies variability between different planktonic microorganisms. And I will illustrate this interspecies variability using analysis from a study which included 18 different groups of microorganisms or biological particles, starting with viruses and then heterotrophic bacteria. And from 3 through 18, these are all photosynthetic phytoplankton species. So the smallest one, prochlorophytes, cyanobacteria, Synecocystis, and then a couple of other cyanobacterial species, and larger species from different taxonomic groups, which are also indicated here. You can see the size or the mean size for all these species, and these data are based on experiments for everything with except for viruses, for which the calculations were done. And there are also some data here on estimates of refractive index, imaginary part of refractive index. But you can see this database encompasses the size range of different particle types, from viruses, which are less than 100 nanometer in size, to the largest species in the database, which is about 28 microns or 30 microns in size. So here you can see this interspecies variability in absorption properties, and 3 different graphical representations of absorption are shown. single particle properties. In this case, I'm showing not efficiency factors, but absorption cross-section. So this is a product of efficiency factor for absorption times the geometric projected area of particle. And you can see here, viruses are not shown. They were assumed in this calculation, no absorption. So this lower curve is heterotrophic bacteria, and the highest, the curve here corresponds to this largest species, about 30 micron in size. Everything from this all these curves, 18, not 18, how many of them, from 3 through 18 are phytoplankton species, photosynthetic organisms. But this is a logarithmic scale, so you know, there's a very, very large variations in a single particle optical property, absorption cross-section, across different species, and it is mainly driven by the increase in size, but of course the absorption coefficient of substance forming these particles or intracellular pigment concentration plays also some role in this interspecies variability. Now, if we look at the very same data, but if we normalize them so we can compare the spectral shapes, you can see very large interspecies variability in spectral shapes. So this one curve, smooth curve here, which shows one maximum around 410 nanometers, is heterotrophic bacteria. So they have no photosynthetic pigments, but they have a small, well, they have a noticeable peak here around 410, which is associated with respiratory pigment cytochromes. Everything else here are phytoplankton species. And you can see major blue and red maxima associated with chlorophyll A, but you can see also a lot of features associated with accessory pigments. The bottom line is you can see very large variability, interspecies variability in shapes. If you normalize absorption coefficients to chlorophyll concentration, which was also measured in these experiments, you can also see very large variability in chlorophyll-specific absorption coefficients. So absorption by phytoplankton, that means it's not necessarily the good proxy for chlorophyll. And oftentimes it is being used as such. And if we look at similar data, but for scattering properties, so scattering cross-section, and the lower left-hand side normalized spectra of scattering to compare shapes, and on the right-hand side normalized to chlorophyll concentration. Again, you can see very large variability. Here viruses are included, so this is the lowest curve, the smallest cross-section for scattering viruses, not surprisingly, very tiny particles. Then heterotrophic bacteria, then cyanobacteria, here Prochlorococcus, and then larger phytoplankton species. You can see very large variability in the shapes of scattering, which we've discussed and explained on theoretical grounds why. And you can also see very large variability if we normalize scattering to chlorophyll concentrations, which is not surprising. Okay, so another level of complexity in terms of optical variability, interpreting, you know, your measurements, bulk measurements that you may execute in the ocean, is associated with intraspecies variability. And this relates to the fact that any species of plankton grow under specific conditions, acclimate to specific growth conditions, for example, to availability of light, nutrients, or temperature. And any single species can actually change its single optical properties quite dramatically if it's acclimated to different growth conditions. And I will only, for the sake of saving time, I can only show a few examples of intraspecies variability. And these are data from experiments with Cyanobacteria synecocystis. On the left-hand side, we have spectral graphs for absorption properties. On the right-hand side, for scattering properties. Different curves have been obtained for cultures of the synecocystis acclimated to different levels of growth irradiance, which are indicated by these numbers, 20, 40, and so on, 14, 50. So the low numbers are low irradiance, and the high values are high irradiance. These are PAR values, photosynthetically available radiation, expressed in micromole of quanta per meter squared per second. But the main message here is that regardless of which optical property we are looking at, whether this is optical efficiency or we have normalization to chlorophyll, or normalization to carbon content, we see very large variability in response to acclimation to growth irradiance. We also see very large variability in scattering. Probably the smallest variability here is, or the most constrained variability is in carbon-specific scattering. And these findings were actually at the origin of some of earlier hypotheses that scattering or backscattering can form a relatively good proxy for carbon concentration in the ocean, that formed the first the basis for proposing the first ocean color remote sensing to derive particulate organic carbon in the ocean from backscattering coefficients derived from remote sensing reflectance. But as you can see, this is still not a perfect proxy by no means. Even for a single species, the scattering per carbon is quite variable. And the second example of intraspecies variability is associated with potential variations induced by day-night cycle. And here you have example data from a diel experiment with a small diatom, Thalassiosira pseudonana. These cells are about 4 micron in size. So you can see experiment that was conducted over 3 days. So night, day. And we have graphs here for the mean cell diameter and also estimates of refractive index over the diel cycle, as well as scattering cross-section that has been measured because beam attenuation spectra and absorption spectra and particle size was measured, so we could derive scattering cross-section. And this is a very important result because you can see that a single species over the diel cycle can vary its size. So generally you can see after sunrise is increasing in size and then decrease. The cells were dividing more or less synchronously in the afternoon. So the size is dropping down and gets minimum before the sunrise, and so and this cycle repeats itself. And very importantly, the estimation of refractive index in these experiments indicates that refractive index shortly after sunrise is increasing sharply and attains maximum near the end of the day and then goes down. And this is associated with the fact that during the day, the cells are photosynthesizing and the refractive index is driven largely by the proportion of cellular water occupied, the fraction of cellular volume occupied by water versus the fraction of cellular solids within the cell. So if you have more water, then refractive index is low. If you have a higher fraction, volumetric fraction of cellular solids, the refractive index will go up. So the photosynthesis is actually leading to the increase of the concentration, intracellular concentration of solids as compared to cellular water. So the refractive index during the day is increasing and then drops down. And as we know from our previous slides, the size and refractive index are major drivers of scattering. You can see dramatic changes of scattering for the single species over just several hours after sunrise. The scattering cross-section can increase twofold. So this kind of data indicate how complicated, sources of variability in the ocean can be. And this kind of variability, these kind of aspects of intraspecies variability and for the most part interspecies variabilities is pretty much ignored widely in many applications, algorithms, ocean color algorithms, and so on and so forth. So I'd like to stress the importance of these data, of these findings, because they really provide a very, very deep insight if what can happen really within the ocean in terms of very many sources of variability, and how the actual true interpretation of bulk measurements of ocean color or bulk measurements of IOPs, how complicated that interpretation can be. I will also briefly show you a few data related to heterotrophic bacteria. So we have data of absorption on the left-hand side, beam attenuation. So beam attenuation is largely determined by scattering. So you can see in different experiments the scattering by heterotrophic bacteria. So we have cells that are about 0.5, 0.6 micron in size. So scattering is higher in the blue than in the green or red. For absorption, heterotrophic bacteria are normally considered to be non-pigmented, and so this dotted line is experiments with typical common non-pigmented heterotrophic bacteria. As I indicated, it only shows this one peak associated with cytochromes, but it turns out that heterotrophic bacteria can contain carotenoids, and such carotenoid-rich heterotrophic bacteria have been isolated from seawater. We just don't know the proportion of carotenoid-rich heterotrophic bacteria relative to other commonly assumed bacteria that do not contain pigments. But in these experiments, we showed that heterotrophic bacteria that contain carotenoids exhibit these carotenoid features. So they may contribute to blue absorption in the ocean if they exist in sufficient quantities. But this question is just uninvestigated. Has not been investigated. We don't know. Another example of particle type. So far, I've been focusing on examples for biological particles, for microorganisms, phytoplankton, bacteria. What about other particles? There are lots of other types of non-living particles, organic detritus, but also mineral particles. I will show you some example of experiments that involved this studies of absorption and scattering properties of mineral species. So several mineral species such as zeolite, kaolinite, or calcite, or quartz, or assemblages of particles, natural assemblages of particles that are dominated by mineral particles that originate from different regions on Earth, like atmospheric dust from Sahara, or some particles in polar regions that are introduced by melting ice, or some other locations or particles originating from soil and eventually can end up in the ocean, either through atmospheric deposition and transport, or with rivers and so on and so forth. So a lot of different types of assemblages can include significant amounts of mineral particles. And without going into detail what these symbols mean, these are different particle assemblages, all of them dominated by mineral particles originated from different locations, but all these particles are suspended in water, and measurements have been made on absorption and beam attenuation. So these measurements also provide scattering as a difference. In this case, we are not dealing, like with phytoplankton cultures, with nearly monodisperse systems. These systems of particles are highly polydispersed, so it doesn't make sense, really. It's not meaningful to determine the efficiency factors or cross sections, because they are so dramatically dependent on size. So if you have very many sizes coexisting in the sample, the meaning of single particle efficiency or cross-section, optical cross-section, is essentially lost. So in this case, in order to compare different, optically compare different types of particles, particle assemblages, mineral assemblages, we are normalizing the measurements of absorption coefficient by mass concentration, total mass concentration of particles, sometimes called suspended particulate matter, SPM. So you can see the mass specific absorption coefficients for different assemblages or pure mineral species at the bottom on the right-hand side, similar for scattering coefficients. And again, without going into detail, if you look at this, there is a lot of variability depending on the composition and origin of these particle assemblages. Typically what you see, mineral-dominated assemblages of particles exhibit stronger absorption at short wavelengths than longer wavelengths. So that is kind of reminiscent of what you would expect from organic detritus as well. Organic non-living particles also exhibit stronger absorption in shorter wavelengths than longer wavelengths. but mineral particles also, although this is not like an exponential type of spectral shape. Scattering can also exhibit different shapes, either increase towards short wavelength or flat, depending on, proportion of small and large particles, or also how refractive index is being distributed between different sizes within the assemblage. And if you look at the color of particles retained on the filters of these different mineral assemblages, you can see some particle samples exhibit this brownish or reddish color. So the main agent, absorbing agent in mineral-dominated particles is iron. So if these particle assemblages contain a significant amount of iron, then they would acquire this kind of reddish color, and they would show this more pronounced increase towards shorter wavelengths in terms of absorption. You can see calcite, or is absorption across the visible wavelength. Pure calcite mineral exhibits undetectable absorption. Pure quartz also exhibits undetectable absorption. So these experiments give you a deep insight into potential variability, potential magnitude, spectral shape of particle assemblages of different compositions that can occur and coexist in oceanic waters. Now, the final group of particles that I want to spend a little bit of time are particles that are in the submicrometer range. We can refer to them as colloidal particles or nanoparticles. And I've already included or discussed a little bit particles in the submicrometer range. I showed you viruses, heterotrophic bacteria, or the smallest photosynthetic phytoplankton, Prochlorococcus or Synechococcus, fall within this range. But in fact, non-living particles, organic and inorganic, are by far more abundant in submicrometer range than biological particles, at least by 1 order of magnitude. However, this is the most elusive constituent in seawater in terms of characterization and quantitative characterization, because in order to understand the contributions of submicrometer particles to optics, you need to know their concentrations, you need to know at least the size distribution, and in the best case scenario also composition. So you could somehow develop an understanding of how these particles contribute to bulk measurements of optical properties in the ocean, including ocean color. There are very few data on particle size distribution, so that's the major determinant of optics, as we know, because it tells us about the concentration as a function of size in the submicrometer range. Here you see example data obtained with transmission electron microscopy in different oceanic regions. So you can see basically on the vertical axis concentration of particles versus size, and the size here is from 0.2 micron to less than 0.05 micron. So we are talking about nanoparticles smaller than 200 nanometers. Again, you can see here pretty large variability in both in the magnitude of concentration as well as shapes of submicron particles. But this technique is not amenable, electron microscopy, for routine use. So, okay, I'm aware only of a few instances where this attempt of count and size small size particles with electron microscopy was attempted and published. Another possibility is to try to use the technique of Coulter counter. That's the electronic instrument that uses electronic principle to count and size individual particles. However, this technique is very difficult to extend this technique to very small nanoparticles. It can work well around 1 micron and maybe down to 0.6 micron. And we've been using it a lot, and we generally do not think that Coulter counter can reliably count and size particles lower than about 0.7, in the best case scenario, maybe 0.6 microns. You can see an attempt to extend the data with Coulter counter here. This is a submicron range from 0.4 to 1 micron. This is a study that was conducted in Northwest Pacific. So you can see concentration of particle versus the particle size in submicron range. But you can see that while the data show this decrease in concentration with size above 0.6 micron, these data tend to flatten below 0.6. So I interpret this as an artifact. This is not a good measurement here in this range. So again, Coulter counter, or is not suitable to cover the entire submicron range, and electron microscopy is not suitable for routine use. So there's definitely a need to develop a methodology to count and size nanoparticles reliably and in a routine fashion in the ocean. Here I'm just showing the results that theoretical results of calculation of scattering, backscattering of submicron particles compared to pure seawater scattering, which is this blue line. And these calculations use the data that are shown in these two previous slides. So with assumption of some refractive index, and using these counts and concentrations and sizes, you can calculate, or you can estimate, the scattering and backscattering. One point I want to make, that these kind of theoretical assessments indicated in this study and also in other studies that colloidal submicrometer particles are a major contributor to backscattering in vast areas of open ocean. They are so abundant that even though they are very small and the scattering cross-section or backscattering cross-section are small, the abundance is so high that they can produce significant contributions to backscattering on the order of dozens of percent, maybe even 50% or so. So this is a very important component. So photons that leave the ocean and are seen by satellite from vast areas of open ocean actually originate from scattering on very small particles in the ocean. So I've been interested in really pushing, the technology to develop an instrument which would be capable of counting and sizing submicron particles in the ocean in a routine fashion. And we develop instrument that uses the technology based on nanoparticle tracking analysis. So if you have small particles, submicron particles suspended in water, they constantly undergo a chaotic motion, which is called Brownian motion, because molecules of water are in thermal motion, then collide with small particles and push them around. So all these particles are moving around. Small particles undergo Brownian motion, which is much faster than larger particles. You can illuminate your sample with a laser beam, and you can collect the information about the Brownian motion with the optical detector. You can actually record a movie of the Brownian motion, and from that movie you can determine the distance traveled by differently sized nanoparticles, and from the distance traveled you can calculate its size. If you also have calibrated volume of measurement, you can calculate the concentration. In other words, you can obtain with this technology the number of particles in the submicron range as a function of size. This is what we are after if we want to advance our understanding of these submicron particles to ocean optics. So we developed this technology that we called MANTA, multispectral advanced nanoparticle analysis, where we use lasers, 3 different colors illuminating the sample, and the detection of Brownian motion is also in different colors. That allows us to better visualize and track Brownian motion of differently sized particles. You can see here a picture of our prototype, and this technology has been actually commercialized. So this instrument is available and has been used recently on the NASA export cruises. So the data of submicron particle size distribution have been already acquired with this instrument at sea. So you can see this instrument in action. You can see nanoparticles in Brownian motion. You can see some small particles moving faster, and you can see larger particles moving smaller. So you can collect movies like this. For example, this is a superposition of 300 video frames acquired during 10 seconds. So each blob here indicates the trajectory of a single submicron particle. You can calculate the distance traveled of this particle per unit time, which relates to the so-called diffusion, Brownian diffusion coefficients, and then from that you can calculate the size of the particle. Also, if you have the volume calibrated, you can calculate the concentration of particles. So my last 5 minutes will be devoted to a few slides. So I have reviewed, I hope I have been able to convey a message that optical complexity within the ocean water is extremely large, and it's because of diversity of particles, their sizes, shapes, chemical compositions. Each of these particle types and each individual particle scatters and absorbs light differently. And this complexity is embedded in this relationship that I indicated earlier for assemblage of individual particles, the linkage between bulk optical property IOP and individual properties, individual particle properties, this Q and G. But I indicated it's just for one single type of particle. In reality, we have countless types of particles. So in order to understand any measurement of IOP, or in fact, IOPs affect AOPs, such as apparent optical properties, such as ocean color or ocean reflectance. So we have to understand how all these different constituents, which are indicated, or types of particles indicated by I, contribute to the sum of these products. And this is extremely, so even though this equation at first glance is simple, the complexity is extremely large, which is embedded in the fact that this concentration of particles of different types varies, and also these individual single particle properties vary greatly according to these concepts that we discussed today. Now, how this problem has been addressed historically in ocean optics. And I have no time really to go in detail. I'm running out of time, but you'll probably learn or you'll be exposed to some of these concepts during this course. Chlorophyll-based approach was one traditional approach widely used over past decades, where optical properties being, or where seawater composition is basically parameterized of a single parameter, chlorophyll concentration. So either IOPs or AOPs, such as ocean reflectance, are being linked, usually empirically, to just chlorophyll concentration. This approach has serious limitations, because at any given chlorophyll concentration, you have a very large variations in any IOP or AOP in the ocean. And even in this typical, commonly used chlorophyll-based models, when chlorophyll is linked to ocean reflectance, you have enormous variability. For any given reflectance value, you can have very, very different values of chlorophyll. Another traditional approach was to parameterize seawater in terms of just few broadly defined constituents: molecular water, W, all particles together, even though they have dramatically different types, dramatically different properties, as you have just seen in my previous slide, or all kinds of dissolved organic molecules also put together in a single component. In the best case scenarios, some particulate IOPs are being partitioned into phytoplankton, but again, typically all phytoplankton together, and all other types of non-phytoplankton particles, NAP. So again, this is a great oversimplification that doesn't account for actual variability that we have just demonstrated in this today's lecture. So if you want really to explain, for example, ocean color in terms of concentration and composition of different constituents, we really need to go a step further. I have been proposing for quite some time that in order to advance the science of ocean optics, ocean color remote sensing, inverse models, it is important. Basically, ocean color science is like ocean spectroscopy. So if you want to do a spectroscopy well, if you want to derive information about some constituent, you need to know the spectroscopic properties of different constituents that coexist in the water. And we are really haven't yet achieved, we are not even close to understanding these spectral properties of most particles, types of particles that coexist in water. The reductionist approach is an approach that offers a pathway towards developing this understanding, and the reductionist approach basically attempts to model the whole system based on the study and understanding of all its fundamental parts or entities. In this case, all fundamental entities would be all kinds of different plankton species, mineral types of particles, organic detritus, and etc. Okay, so I am at the end of my lecture, so I will skip, but few slides that I have to skip because I don't want to keep you beyond the time I have allocated. Basically shows how powerful the reductionist approach is in developing understanding how different types of particles contribute to absorption. So you can build a budget of scattering, total scattering, absorption, or you can also develop an understanding how a specific mix of particles affect ocean color. And the several slides show the examples of these reductionist models. Here we have 21 components that are being put together, and we can develop absorption budgets, scattering budgets, how different particle types, different planktonic organisms contribute to absorption or scattering. We can also run radiative transfer simulations in which we have a mix of particles. If we know single particle properties and concentration for each type of particle, we can create a mix of these particles, run the radiative transfer model, and we can answer the questions: in what ways does variability in detailed seawater composition determine variability in ocean reflectance? Or what information about water constituents and optical properties can we hope to extract reliably and accurately from remotely sensed reflectance with acceptable accuracy? And the last slide. So my main message is this: I've highlighted the complexity of seawater and optical properties of seawater in terms of detailed composition, different particle types, but this complexity should not deter us from pursuing the proper course in future research. And my closing statement is this quote from the work by Steven Weinberg, who received Nobel Prize in Physics in 1979, and this quote comes from Dreams of a Final Theory. So Steven Weinberg basically worked on the elementary particles in physics and attempted to develop a theory of understanding of how universe works in terms of basically reductionist approach, understanding of the universe in terms of its basic entities, elementary particles. So the reductionist worldview has to be accepted as it is, not because we like it, but because this is the way the world works. So thank you very much.